So first of all, thank you everyone for coming to this One Word Game Theory seminar. I'll be presenting Yevgeny. It's my honor to present Yevgeny, who will give the junior talk. So Yevgeny is a very diversified researcher. I mean, he's diversified as it gets. He started off his master's in physics. He actually specialized in astrophysics. And then during the PhD, he came to join us in game theory. He did his PhD under supervision of Ehud Lerer in the School of Mathematical Science in Tel Aviv University. His PhD, he specializes in repeated games with some stochastic component where the one player or maybe two cannot revise their actions all the time. It's called an asynchronous games. And this talk will be somewhat similar. He's now doing his postdoctoral, he's a postdoctoral researcher at the Axe-Marcel School of Economics for 2 years now, or 1.5, and finishing in about a year and a half as well. And so, Yevgeny, thank you very much for the talk. Good luck.
Thank you for introducing me. Thank you for having me here. And thank you everyone for zooming into my talk. Today, I'm going to present you a paper joined with Xavier Venel and Anna Zhleva about repeated games with switching costs. And our main focus of this paper is about the comparison of stationary and history-independent strategies. Now, naturally, I don't have a lot of time, and the medium of Zoom is a little bit, has its boundaries, so I'll focus on the main ideas and main results of the paper, and if you want all the details, I can send you a draft or we can talk later. So what this paper is about and what is our main focus. In many economic models or game theoretic models, there is some sort of intertemporal dependence. So actions that are played at one time instance somehow affect our ability to play in another time instance, or maybe the payoffs in the future. And here we add such intertemporal effect to the well-known repeated games. We focus on zero-sum repeated games. And what we do, we add switching costs. So basically, when someone does not repeat his yesterday's action, he pays some fine for changing his action. Now, similar models for different, for non-repeated games, for other sort of economic models were studied, and I don't want to talk about them here, but very similar models to our model of repeated games with some sort of a switching cost were studied before. For example, Lippmann and Wang focused on non-zero sum games, and they did several variations, whether it was a finite horizon or maybe infinite horizon with mostly discounted payoffs. Here, as I said, we focus on zero-sum games, and a similar model to ours was already also discussed previously, first by Sean Makers and his colleagues in 2008. They framed it a little bit differently. They gave bonuses for players that replay their action instead of finding players that change their actions, but this is identical. The idea is identical to ours. At some point, we basically generalize them, and at some point I will tell exactly where their model is a private case of ours. In addition, this model is very natural to cybersecurity, and there's a series of papers that discuss how this model should be solved and analyzed in the cybersecurity literature. What they do is they only talk about an approximate solution. So what we try to do in this paper, we try to solve this general model and give some sort of results about the exact solution, and also compare the exact solution to the approximate solution and understand what is lost when you approximate. I will start with introducing formally the model, and then I'll show two examples that kind of capture the entire picture, and also make it very clear how this model represents something in cybersecurity or security literature in general. So, as I said, we have a repeated game, a repeated normal form game. A is the payoff matrix. Player one is the maximizer. She chooses rows. Player two is the minimizer. He chooses columns. The entire paper and the entire talk are from the point of view of player two. So we try to minimize and we try to lower payoffs as much as possible. And to player two, we also add a switching cost matrix. This is S, which is an N by N costs matrix. And there is also a parameter C, which is a multiplicative parameter. One way to think about it is just some sort of a weight that we give to the switching cost relative to the stage payoff of the game A. And when we change this weight, we can receive different behaviors. The game is played as following. Every stage, the players choose their actions. So player one chooses rows, player two chooses a column, and the payoff that player two plays to player one is the payoff, the regular payoff in the matrix A, and also C times SKJ, which is the switching cost, and K is the pure action of player two yesterday. So if player two played K yesterday and today chooses to play J, he needs to pay SKJ. Now, this idea that player two pays to player one can represent either some kind of a worst case analysis of player two, where for him, player one is an adversary and he wants to know how low he can go. Or in some cases, this is a real payoff that player two pays to player one, or maybe it's the real goal of player one to make player two to pay as much as possible in the idea that if I make my opponent go bankrupt, this is good for me, even if it didn't really pay me this switching cost. So far, it was all sort of in pure language. Of course, player can use mixed actions to choose their action, and the expansion to mixed action is standard with the expectation. The only thing that we need to remember here is that when players choose their actions today, the action of player two yesterday is well known. So this K is known even if it was chosen in random. And both players know it. This is common knowledge, and then they can then base their actions today on the pure action of player two yesterday. We consider an infinite horizon, and for us, the payoffs are undiscounted. We use the lim-inf criteria to assess the stream of infinite payoffs, but other criteria will work just as well. A few small assumptions and normalizations just to make the results look prettier. We normalize the game A to be between 0 and 1. So this is a standard thing that we can do without any loss of generality. We assume that the matrix S of the switching costs is non-negative. So all the entries are 0 and above, which means that basically there is no incentive to switch to a particular action. And a non-zero entry, the lowest non-zero entry is 1. Again, this is normalization simply because in the end, we take all these payoffs and multiply them by C. So C can take care of any such thing. And our last assumption is that replaying the previous pure action is costless. So the diagonal of S is all zeros. And how this game can look like. So here is an example which represent maybe the cybersecurity or security issues that lead to this kind of model. Player two in this model is a security guard. He patrols between 4 warehouses. S represents the distances between the warehouses. It is possible that they're not symmetric. So maybe getting from 3 to 4 is easier or shorter than from 4 to 3. And C can be interpreted here as petrol costs per unit. So C times the entries of S is how much petrol is paid to get from one point to another. Player two is an attacker. He can choose in each time step which warehouse to attack. He can also do nothing. And the payoff and the loss of the guard has the two components. First, the switching cost, the movement cost that we talked about. And the second is just the cost of what happens when he is in location J while an attack is being carried out in location I. And what we're interested in this kind of game, the most basic thing is to know what are the optimal strategies, what is the value of the game, and how both players play. In particular, what we will do, we will assume that both S and A are fixed, and the only thing that changes is C. And then what we will want to do, we will want to know how all these things in the game change as a function of C. And to demonstrate it, I want to show you an example with numbers this time. And consider this simple rock, paper, scissors example. I didn't normalize A just to make it more clear and standard. So the game is rock, paper, scissors. The switching cost matrix is a uniform one, meaning that all actions that are being changed are changed with a payoff of 1. There is no preference to any other. And what we want to know what are the optimal strategies here. So when C is relatively small, from 0 to 1, the optimal strategy for player 2 is simply to choose all the actions with probability 1/3. This is the regular optimal strategy in rock, paper, scissors. And here, the fact that there are switching costs don't matter to him. He pays them, the value is 2/3 of C, but he plays as if there are no switching costs. At some point, and this point is C equals 1, playing third is too costly for him because he switches too often and he pays too much switching costs. What he has to do, he has to reduce the probability of switching, and it turns out that the new optimal strategy is to replay the previous action with probability 2/3 and to play the action on the right, and this is done cyclically, with probability 1/3. Again, as we increase C, switching becomes less and less profitable. And in the end, at C equals 2, switching is too costly. At any probability, in any frequency, switching is too costly for player 2. So what he has to do, he has to choose one action and never switch. And then, of course, player 1 best responds. The payoff is 1 forever, and it doesn't no longer depend on C. And this is kind of the exact solution, both the value and the optimal strategies that we want to investigate in our first part of the paper. So let's start, let's go to the results and generalize this example. Most of the things that I in this slide already exemplified them on the previous example, so I'll go over them a little bit briefly. This game is equivalent to a single controller game where the actions in the stochastic games are the previous actions of player 2 or the previous last action of player 2, because this is the only payoff dependent information. And we know that in this kind of games where only one player controls the states, there is an optimal stationary. There is a value and it is attained in optimal stationary strategies. This was already proven in the 80s by Filler and Ragawan, that also provided us with an algorithm of one way to calculate the value. Now, as I said, we fix A, we fix S, and our first result says that when we change C, the value of the game as a function of C is an increasing function, continuous, concave, and what is most important here and interesting is that this function is piecewise linear with finitely many changes. Moreover, in each such linear segment, player 2 has an optimal strategy that is independent of C. So basically, to play optimally, player 2 needs to know only in which segment he is. He doesn't have to know the exact value of C to do so, which gives us both robustness And it gives us the ability of not changing the strategies if C changes. So if you think about the security guard and maybe the petrol costs change a little bit, he does not need to adjust his entire strategy. He can do whatever he did before, just as long as the change in C is small enough. In addition, a consequence of this proposition is that the set of candidates to be optimal strategies is finite, and it depends only on A. It does not depend on C and S. So in theory, I can write a list of all the candidates. It will be a long list, but it will be finite. And then for every C and S, test all of them and choose the optimal action. Now, the problem with stationary strategies is that at some cases they're too difficult to compute. For example, for a stationary strategy, you need to choose which mixed action to play after each action. So you have n square order of n square parameters. And in some applications, they try to simplify the strategies used, and they use static strategies. Static strategies in this context are strategies that are just independent of the state, basically choosing one mixed action and replaying it over and over again. To define a static strategy, we need much less parameters. And the other pro for this kind of strategies is that in some applications, they are the only ones that are permitted. For example, in the cybersecurity literature, they have some arguments why they do not want to base their action on the previous one, but they want only to do one mixed action forever. Now, if we consider static strategies, we can actually write the stage payoff in a much nicer form. And the thing is that in static strategies, the value might not exist because we limit maybe the strategies to a set where there is no optimal strategy. So instead, we consider the min-max value, so the minimal value that player 2 can guarantee. And clearly, it is much more than the value of the game in stationary strategies, which again, more is worse. And what we do in the rest of the paper is we discuss this bound and try to answer the question by how much player 2 loses by limiting himself to static strategies instead of stationary. Now, our results in the paper is a list of bounds for different cases, starting from the general case, which I will leave in the paper and not in this presentation, just because it has too many letters. But the more we assume on the game, the more knowledge we have about the different components of the game, the more we can simplify the bound or maybe make it tighter. So if S is symmetric, the bound will depend on the difference between the value in stationary strategies and 1, and also this maximal switching cost. Or if all the costs are equally costly, for example, as in the rock, paper, scissors, this can be even more simplified into the following bound. And this kind of model, the one in which all the costs are equally costly, is the one that was studied both by Schoenmakers in the zero-sum case and by Lippmann and Wang in the non-zero-sum case. So one of the main, let's say, generalizations of this paper is that we consider all kind of structures for the switching costs and not only the equal one. Now, I think I will skip this bound, which also gives us an additional bound when we assume that there are no free switches. So meaning that in the end, switching is too costly for C large enough, and then you play purely regardless of whether you started off playing stationary or static. And I will just skip to the summary and just add a few words about our future intentions. So as I said, what we did in the paper and what I showed you is how we is how to find the value and the optimal strategies in the stationary game. We also show how to do it in static strategies, but I didn't show it here because there's a time limit. And what we also do is we bound the difference between the two and try to assess how much is lost because of the choice to use this more simple strategies, the static strategies. What we also do, and I find quite interesting, we generalize all this discussion to general stochastic games. So here we discussed only games that are born in a very specific way of taking a normal form game and adding switching costs. But in general, we can discuss any stochastic game as long as all the actions are available in all the states, and ask what happens if in this stochastic game we play statically instead of stationary. And we can bound this difference here too and give different results in this case as well. For the future, we want to use this paper as sort of a benchmark for non-zero sum games. And there are different methods of how to turn this game into non-zero sum, whether allow both players to pay switching costs or assume that the switching costs of player 2 are not paid to player 1, but rather to the bank, or similar ideas. And also another idea is to add switching costs, but base them not on the previous action, but instead on the previous payoff. So this kind of models a situation where a player, let's say, wins in a certain round, and then he chooses that this action was good for him, and he's reluctant to change it. And this is a fact that people saw when let real people play rock, paper, scissors, that once they win, they want to replay this action with higher probability, although it's not really a better one. And another extension, and actually kind of a sister project to this one, which we started it and then moved to this one, and now we're going back, is an extension to parallel games, where players play several games at the same time, but it can, in every time step, can choose only one of the games, and only there they can change their action. And although it's not similar to switching costs, but a lot of the ideas and the mathematics there and here is the same, and we can use the results. I think I'm kind of up, so thank you for listening.
Thank you very much, Yevgeny. So we don't have much time, so if there's one quick question for Yevgeny.
Well, may I ask one? The most surprising thing was that within the regions, the optimal strategy doesn't depend on the value of C. I could have imagined, my first guess would be it would depend kind of smoothly on C. Can you give us some idea why it stays constant?
So I'll try to give the intuition in this example. The idea is that, well, and first of all, I want to say the important thing that this is only true for player 2. Typically, player 1 in every time step, for every C has to choose his actions accordingly. So for player 1, it is really smoothly changes with C and C dependent. And the idea here is that basically what player 2 has to do, he has to keep player 1 in the stochastic game that results from adding the switching costs and so on, independent between his actions. Now, player 1, because the same switching cost is added to each column, player 1, he sees them in the sense that he pays them or receives them, but he has no effect on them. When he chooses to play top or bottom, the C component of the actions is the same. So when player 2 chooses an action that will keep player 1 indifferent between the rows, he does not need to depend it on C, because player 1 will have no preferences regarding the C component. Okay, so he has to do it only according to the game A, and player 1 in return has to use C to make player 2 indifferent because player 2 is affected by the Cs. And this breaks down here, the 1 and 2 happen when player 1 can no longer keep player 2 indifferent between all the actions that he's playing, and then some actions become dominated.
Good, thank you.
Okay, Yevgeny, thank you very much for this great talk. Thank you, everyone. It's been a pleasure. And if anybody has any more questions, Yevgeny would love to answer them later on. Send them, check his website, and nice photos as well from France.
Okay, we take 5 minutes break and then we come back. So 5 minutes break.